Thanks for tuning in. I recently recorded a podcast with Rob Akers, the UK Atomic Energy Authority's Director of Computing Programmes, about a new £45 million, 1.4 megawatt supercomputer called Sunrise. So, Rob, how powerful is Sunrise?
So Sunrise is a new supercomputer that's tuned at the interface between high performance computing and artificial intelligence. So to answer that question accurately, I'd have to define the floating point precision of the machine. But in terms of it being a machine for AI, the floating point 8-bit precision of the machine means it's about 6 exaflops. So it's an incredibly powerful machine which could be used for inference and for a lot of AI applications. And then at the other end, at the 64-bit precision, I think it's something like 50 petaflops, something like that. So it's not as powerful as Isambard AI, the other big machine that we've got at that confluence of AI and HPC at the moment. But yeah, it's an incredibly exciting machine, tuned to do some incredibly exciting problems.
I was reading the press release, and it's saying that it is the most powerful in the world to do a certain type of application. Can you, without going into too much detail about all the research that's going on at the UK Atomic Energy Authority, at a very high level, what is it going to be doing for us and for you?
It's some way off that, but it is the most powerful machine, we believe, that has been dedicated to solving fusion problems. So it's going to be, at least for a short while, I think it'll be the second most powerful supercomputer at UKAEA level in the UK. But the most important thing is it's designed to do both AI and high performance computing, because without the AI, our problems would be intractable for the amount of money that we currently have available. So it's a very exciting machine built on AMD MI355X GPUs, which are kind of tuned at that confluence of AI and HPC.
Um, are you able to talk about how much, the specs, how much memory it has, or how much storage, or bandwidth? I don't know how you would describe a supercomputer. It's not something I come across. It's not something you can review, right?
To define how powerful a piece of hardware like this is, because it depends on your metric for success. This machine has the full spectrum of floating point precisions from 8-bit right the way up to 64-bit precision, and each one of those targets a different part of the problem. But the important thing for us is that we can't forego 64-bit precision, because that's what's going to feed the artificial intelligence algorithms that we'll be applying to this. The AI is what makes it tractable as an engineering tool, because the AI will collapse those high fidelity models that need that very high bit precision down into what we call surrogate models, which can run on a workstation or a laptop in a tiny fraction of the time that the big solvers work at, typically on those larger supercomputers. So it's almost like an instrument for discovery. You think of it like that. It's almost like a facility. It's not like a laptop, just a very powerful laptop. This is a very complex piece of machinery that we'll be putting to the task of solving a very large set of very complex problems.
Okay, but excuse my ignorance for this, Rob, but one of the things you said right at the start when I asked you about how powerful it was is that you mentioned 8-bit, and I haven't heard about 8-bit since I was 12 years old. Programming a BBC Model B or something. Whatever it was. What does that mean for you? What is 8-bit in terms of why it's very important for the work you're doing?
Yeah. So look, yeah. I'm of that generation, 8-bit computer games. Yeah. The interesting thing is that 8-bit precision has become an incredibly powerful part of the computing landscape now, because of large language models mainly, and we are going to be doing work in that space, building very bespoke models that will ingest text corpora, document archives that have been collected over many, many decades, and turning that into useful information and knowledge. But we want to put that together with the experimental data that we record on facilities like MAST, the tokamak that we run here at Culham. And working out how to do that, again, needs that full spectrum of precision. So the 8-bit tends to focus towards the large language models, and particularly inference, so running those models. And then as you move up that ladder to 64-bit precision, you're moving into the realm of high fidelity simulation that needs huge accuracy because of the way we run models forward in time, and we can't allow them to drift in terms of preserving certain physical quantities that mean those simulations are meaningful.
But without going into binary, so 8-bit means reading characters.
It's very limited. It's very chunky in terms of the discretization of the space that you're representing, if you like. So we use FP8 precision as a metric, largely because we're comparing with other AI machines. But it's not the best metric for an AI for science machine. That's fair to say.
And just finally, one of the things that I read about Sunrise is it's going to be doing digital twins. Very, very briefly, what does that mean for you and the work you're doing?
Okay, so so there's a range of definitions for what is a digital twin. We use a kind of a very specific definition. It's actually the definition that NASA uses, attributed to Vickers and Greaves. Vickers and Greaves. And what it is the ability to simulate very high fidelity models, very importantly, strongly coupled models. And that's because in a fusion power plant, there are lots of different physical mechanisms that couple the plant together, everything from structural forces due to gravity, but also due to electromagnetism. And then there's a lot of heat flow and there's a lot of radiation flow across the system. And everything's coupled together. Historically, we've not been able to simulate that at scale. So what we, I guess, worry about is black swans or emergent behavior that is a result of that coupling. So the digital twins we're talking about are about modeling very complex systems and using those models to compare with reality to tune up our ability to step forward in time or to step forward or step outside of where we've been before with those facilities, or indeed to create new pieces of machinery that we've never seen before and take a giant leap where we have confidence in having nailed down the known unknowns in those simulations because we've put that coupling in, that physics, that multi-scale physics that was missing on older supercomputers. And so the idea really is that we'll reduce the amount of test-based design that we have to do, and test-based design is expensive and it's slow. So it will allow us to basically take on a moonshot-like problem, but a lot more cost-effectively to reduce risk and accelerate the time to delivery of commercial fusion devices.
You can find the podcast and full article on www.computerweekly.com.